Hello everyone, I'm pleased to introduce our recent work published in Navigation. The motivation behind this work comes from the growing demand for low endurance, high precision navigation across many domains. Inertial navigation systems are attractive because they are self-contained and highly reliable, but their accuracy is always limited by the accumulation of errors from gyroscopes and accelerometers. Rotation modulation has emerged as a cost-effective method to suppress error drift and to enhance long-term navigation capability, and this is the foundation on which our work builds. Previous research has typically handled calibration in the vertical coordinate frame. Some methods attempt to calibrate both MU and turntable non-orthogonality directly from navigation errors. However, the propagation of non-orthogonality errors is complex and difficult to observe. As a result, the calibration time required for non-orthogonality is often much longer than for other error parameters. Other methods first calibrate MU errors and then address turntable errors. However, such a scheme results in more parameters and need to be calibrated, which also reduces convenience. To address these issues, we developed a mathematical model for dual-axis rotational INS. We defined the relationships between these frames and introduced a non-orthogonal angle between the two rotation axes. Our analysis shows that non-orthogonality has two distinct impacts. During calibration, it couples into the estimation of MU biases and installation misalignments, leading to inaccurate results. During navigation, it produces periodic oscillations in attitude and velocity errors, and the size of these oscillations depends directly on the rotation angle. A useful mitigation is to employ symmetric variations of the inner gimbal axis, which can effectively reduce calibration errors. Based on this understanding, we propose a new calibration method that combines multi-operation management, gyroscopes, rotation calibration, and reverse error corrections. We first tested our approach through simulations. Monte Carlo experiments was performed with non-orthogonal angles ranging from 1 to 40 arcseconds. The results showed that our method consistently achieves higher accuracy in estimating accelerometer bias and misalignment errors. Compared with other approaches, our scheme is both accurate and robust, while the six-operation method is highly sensitive to non-orthogonality. And the system-level approach, although more stable, is less precise for installation errors. The chart presented here shows its comparisons clear. We then built an experimental setup to further validate the method. A fiber optic inertial navigation system was mounted on the dual-axis rotation platform. The stability of the platform was confirmed through Allen variance. In the calibration stage, the MU was placed in 12 symmetric orientations, each maintained for 100 seconds, while the gimbal rotated at a speed of 4 degrees per second. Finally, the experimental results demonstrate the effectiveness of our method. The proposed scheme produced the lowest oscillations in attitude, velocity, and precision, and the no-separation error remained below 1 km over a 6-hour navigation test. By contrast, the six-operation calibration exhibited large oscillations and poor accuracy, while the system-level approaches achieved some improvements in velocity estimate but was less accurate overall. The chart illustrates its comparative findings, showing the clear advantage of the proposed scheme. For more details, you can refer to our paper published in Navigation. If you have any questions or would like to discuss further, please feel free to reach out to Dr. Yilan Zhou at the email address provided. Thank you very much for watching.